Hey all, here is the lesson video for exponential functions for 9.1. You can read the objectives at the top here, but essentially this is going to show you what we're really working towards with this lesson. So quick review of exponent rules from Algebra 1. When we have two things with the same base and we're multiplying them with different exponents, we're going to add the exponents. When we have an base to an exponent raised to an exponent, we're going to multiply their exponents. When we divide something, we're going to subtract their exponents. And then when we have a multiplication term raised to an exponent, we're going to distribute the exponent into both of those terms. Notice we can only do this over multiplication. If there was an addition sign in the middle, we would have to use our foiling methods. Excuse me. If we have a base raised to a negative exponent, we're going to write that as 1 over the base to the positive version of that exponent. Essentially, it flips it to the denominator of the fraction. If something starts in the denominator and has a negative exponent, we're going to flip it up into the numerator. It's going to be x to the a. Notice this becomes positive and it's no longer a fraction. If it's on top, it flips it down. If it's on bottom, it flips it up. So let's just do a quick review of that, and we're going to throw a few square roots at you just so you remember those skills as well. So this first problem, 3 to the square root of 2 to the square root of 2 is going to be our rule 2. We're going to multiply those exponents, therefore getting 3 raised to the square root of 4. However, when we simplify that, it becomes 3 to the root 2, or just 9. This next one, when we divide, we have to change this around a little bit. I'm actually going to write it as a fraction like this. I think this sometimes helps us. Now this looks a lot like our rule 3 where we want to subtract the exponents, but we can only do that if we have the same base. They have to be the same x here. So you'll notice 8 and 2 are not the same. So before I can just subtract those exponents, I have to rewrite one of these to get the same base. I know that 8 can be written as 2 to the third. So I'm going to rewrite that. I'm going to say 2 to the third to the fifth. That just stays up there. Over 2 to the fifth. Now that they have the same base, I can subtract them. Remember, I leave the base alone. You see this? Bases, the x stays the same. We get 2. 3 square roots of 5 minus 1 square root of 5. If these were x's, it would be 3x minus 1x. I'd get 2x. However, in this case, I get 2 roots of 5. And that is my final answer. All right, next one. We've got multiplication going on here. However, I see a little bit going on with this m, and I want to simplify that before I multiply it. So I know that root 28 can be simplified to root 4 times root 7, which is the same thing as root 2, 7. And then we just leave the second one alone. Simplifying that just makes it a little bit easier because now when I multiply them, I'm just adding the exponents, and adding 2 root 7 and 1 root 7 becomes 3 root 7. I couldn't add them before because they weren't like not like terms. They weren't similar values there. They didn't have the root 7 on top. So it becomes m to the 3 root 7. All right, last one here. This is going to be our rule number 4, where if we raise 2 values to an exponent, we just multiply that into both terms. So this becomes x to the 4th. This becomes y to the 3rd to the 4th. Those both simplify to 2, and I get x to the 2, y to the 6th. And that is my final answer. If you need a quick review of exponents, radicals, there's a great one out there on CK12, and I'm sure Khan Academy's got one as well. So let's take this into a real-world application. March is just around the corner. I'm sure some of you take part in the March Madness brackets. This is the NCAA bracket from 2017, I believe. So the NCAA men's basketball tournament begins with 64 teams and consists of 6 rounds of play. So there is a playing round. We're going to leave that out. And essentially, the bracket to the right is going to show what occurs. Now, I know it's hard to see, but again, you could Google it. You get the idea here that 2 teams, they play, then 1 team, they play the winner of the next one. It goes on. So can we write an equation to represent the number of teams, T, that competes in a tournament of R rounds? Well, since we know that 64 teams compete in 6 rounds, we know there's got to be a little bit of exponent rules going on here. So one way we can model this with an exponent function is T, the teams, is equal to 2, the 2 teams that compete, to the R, where R is the number of rounds. And we could actually plug this in and see that this is true. 64 is in fact equal to 2 to the 6. Now, why does this work? Well, because each time 2 teams play in a round, we multiply that to get one of these single brackets until we have all of these games represented. All right, we're going to now define an exponential function. So an exponential function is an equation with a variable power. And variable power just means exponent. And the general form, I think, is what's more important in this case, because this is what we're going to be working with a lot more. And it's y is equal to a times b raised to the x. Why do we write it this way? Well, the a out in front is going to represent a coefficient, and that's actually going to change our exponent rule quite a bit. So we want to be aware that the exponent is out in front. It's not part of the base itself. All right. It's time for a little calculator Desmos. Since I can't switch over to Desmos, I'm going to do it on my calculator, and I'm going to bring it in here. I'm actually going to show you how to use this to graph function as well while we're at it. So it says graph the exponential functions of y equals 3 to the x and y equals 1/3 to the x on the same screen. All right, so I've cleared my calculator out. If you want to see how to graph, we're going to go up to this y equals button. And I already have 2 in here, but I'm going to clear those out for you. So my first function is 3 to the x, and I can put that one in as 3. Let me see if I can bump this up so you can see it. I don't want to get too much here. This one is going to be 3 to the x. The next one I'm going to put in is 1/3 to the x. I'm going to put this one in parentheses so that we know that the x is going to both of those. And then I'm next going to go to my window, and I'm going to give a really small window so we can see what's going on here. I'm going to go from -5 to 5 in my x min and x max. I'm going to go from -5 to 5 in my y min and y max. There's some other buttons up here. Those are kind of cool. They're really helpful for the ACT, but I'm not going to go into those right now. Once you're ready, you can just hit graph. It's going to take a minute. It's loading up here. So that is our 3 to the x. You can see that one goes up. That one is our 1/3 to the x. So how do the shapes of the graphs compare? Well, they're relatively the same. One just goes down, one goes up. So I personally, if I was taking notes, I would show these graphs and see what they look like. I'd label this one 3 to the x. I'd graph the other one as starting up here and going down. This one's 1/3 to the x. And I would just say that they basically look like mirror images of each other. So do the graphs appear to have asymptotes? Well, we can't really tell what the asymptote is for either of these going in the x direction, but it's pretty clear in the y direction that they're getting really, really close to 0, but they're never really going to touch it. So do they appear to have asymptotes? Yes, and I would say that the first one is y equals 0 for both of those curves, and you can say that for both curves. The other thing I want to notice is how do the y-intercepts of the graph compare? So where do they cross the y-axis? Well, in this case, they both cross at the 1 mark. So I would say for the y-intercepts, the y-intercept is 1. And the cool thing about this is that 1 is actually the a value. So 1 is the a value in our equation. Writing without pushing the calculator off here. So describe the relationship between the graphs. Why do you think one curve is rising and why is the other one falling? Well, if you've heard about exponential growth and decay, that is actually the relationship. So we grow, there's exponential growth when our base, our b, is greater than 1. So 3 to the x is going to be a growth curve because our base is above 1. And as that increases upwards, it's going to eventually reach some sort of asymptote here, but it's always going to be going in the up direction. We're going to have decay when our b is either between 0 and 1. Now, when it's less than 0, we'll deal with that a little bit later. But the idea here is that if you have a fraction as your base raised to the x, it's going to be a ever decreasing curve. So I just want to re-note that what we've learned so far is that a is the y-intercept, and then b tells us whether we have growth or decay. Just something good to know. All right, we're going to clear the screen now, and we're going to graph these two as well. So I'm going to go back to my y equals. I'm going to clear those out. In the first one, I'm going to put 3 times 2 raised to the x. Notice PEMDAS says I have to do an exponent first and then multiply, so you cannot put this in as 6 to the x because it will not be the same function. Same thing with my second graph when I have a negative 3 times 2 raised to the x. This is not negative 6. I have to do my exponent, then my multiplication. I'm going to keep the same window for now. Let's see if that works. And I'm just going to hit graph. All right, first thing I notice with at least one of these functions is that it has a y-intercept of 3. It looks like the second function I put in, this negative function, ended up flipping it over the axis. So I'm just going to write those down. A is the change, or it changes the y-intercept. So you see when there's a 3 out in front of our function, it changes where we cross the y-axis. The other thing I notice is that a negative changes where it reflects. Changes where A, I'm going to move this out, reflects over the axis. So if we just take another quick look at this one, our first graph, when it was positive, went through at positive 3. When we throw a negative in front, it just drops it down to negative 3. Maybe sketch a quick summary of that. If you want to draw some pictures down here just to highlight what's going on. I'm not going to just for the sake of time, but I would encourage you to do so. So let's do a quick summary of what we learned in this first part of the lesson. We have 2 types of exponential functions. We have growth. That's our first type. That is when b is greater than 1. The second type we're going to have is decay. That is when b is between 0 and 1. And why do I only go down to 0? Well, I told you I'd hint on that later. It's because when we're below 0, we're going to have very similar properties. They're just going to be flipped over that the x-axis. So we can say, or when b is greater than 1, but x is negative. So b to the negative x is one of those instances where we flip. An example of that would be 2 to the negative x equals 1/2 x power. Notice how when we have a negative exponent, it then flips it, turns it into a fraction, and raises it up to that x. And then there's just a picture over here as well that you can look at a little bit. So I highly encourage you before our next lesson to maybe go and check out some of this on Desmos. Play around with it a little bit, mess around with your calculator. If you have any questions on the lesson or on your calculator, please don't hesitate to ask. This can be a tricky lesson.